You may be used to the quantity work done as force times distance. So here's a car being moved by force, certain distance, and the work done, W, is the product of the force multiplied by the distance travelled. Here's another example. The force is being provided by Earth's gravity on an object as it accelerates a certain distance towards the Earth. Now so far we've treated the gravitational force as constant, but that's because we've been zoomed in to such a small region of space that the variation in gravitational field strength, little g, is negligible. Here though, over the distances we're dealing with, g is not constant. It's given by this equation here and graphically shown here. So over the distance that the object travels, the value of f changes significantly. And so if we're trying to calculate work done, what value of f should we use? Well, in general, we should split that distance travelled up into a series of infinitesimal distances over which for each of those distances there's a value of f that works and is constant over that distance. So here's a small distance, not an infinitesimal distance because we can't draw those, but here's a small distance, delta x, and a value of f at that point. Then when we multiply f by delta x, we get the area of this green rectangle, which is an estimate of the work done moving the small distance delta x. But when the object's moved that small distance, then it's in a different place and the value of f is different. So we need to use a different value of f to get the next small green rectangle for the next little bit of work done, and so on and so on. Adding up all the small green rectangles gives an estimate of the work done travelling from the start to the finish. Now that small green rectangle is equal to the value of force multiplied by the small distance, but the total value of work is only approximated by those small rectangles because the small rectangles are only an approximation to the area between the x-axis and the blue curve. Look at the missing bits of area here. So the way we're going to cure that is by shrinking the small distances delta x down to an infinitesimal distance. And mathematically that means that the sum of small rectangles is replaced by the integral of the force f with respect to the distance from point x1 to point x2. And that's the main point of this video. We'll carry on for a bit to see how that works out and gets us an answer, but this isn't a course on how to do the integration. We're trying to explain what the integration means in the first place. So what would we do? Well, we know how f depends upon x. It's the equation in red, and the x squared in the denominator is equivalent to a power of x to the minus 2, and what happens is that when we integrate that turns into a power of x to the minus 1 with a minus sign, and substituting in the boundary values gives us this equation for the work done. Now because x2 is smaller than x1, that means that the work done is greater than 0, which is what we'd expect because the force F is doing work on the object which increases its energy, in this case kinetic energy, and makes it go faster, which is what we know happens as things fall towards the Earth. Now if we do the same approach for a trivial example, you'll see the connections. We already know for the car that we didn't bother using integration for that. We just said, well, the work is the force done multiplied by the distance because the force is constant, so we don't have to worry about infinitesimal distances and adding them up. But we can still do that. So here's the force multiplied by an infinitesimal distance and then small green rectangles, if you like, added up between x1 and x2. And because the force F in this case is constant, then integrating F turns into Fx, and between the boundary values you have Fx2 minus Fx1, which is F multiplied by the distance travelled, which is what we knew in the first place. The point is that the integration method isn't just some magic thing that you invoke when things change. It's there all the time, but you don't have to use it when the force is constant. Now, as another example, you might have learned about the quantity impulse. Where work done was a force multiplied by a distance, impulse is a force multiplied by time. It's a useful quantity because it provides a change in momentum, and it's often given as F delta t, so force multiplied by the time interval for which the force acts, and that is equal to the change in momentum that the force produces. So here's a graph of force against time, and here's a large force acting over a small time interval, and also a small force acting over a large time interval. And the area underneath the curve of the large force for a small time interval is the same as for the small force for a large time interval. And that's because the forces are constant and because the ratio is 5 to 1 compared to 1 to 5. It's not generally true. We've just picked this as an example. But the point is that those two forces acting over those two time intervals will increase the momentum of the car by the same amount. An example of momentum where a force isn't constant might be, for example, a golf club hitting a ball, and here is a model of the force on the ball from the golf club. It's certainly not constant. Now, what would we do here to work out the change in momentum of the golf ball? Well, just like before, we can look at small time intervals, create rectangles, add up all the rectangles, and get an approximation to the change in momentum. And of course, as we shrink the time intervals, we get better and better approximations to the blue curve until when the time intervals in the limit go to 0, we model the blue curve exactly. And then instead of a sum of rectangles, we're dealing with an integral of the function for f.